Hello, my name is Christina Jimenez, and I'm a developer at GreenPace. Today, we will talk about our security policy here at GreenPace. So, let's get started. Okay, so defense in depth. So, let's talk about our defense in depth at GreenPace. Our security policy is a formal list of secure coding standards that we use to address vulnerabilities in our software development process. Since we're dealing with sensitive information here, it's our top priority to implement efficient security controls that prevent common threats in the industry, not only for us, but all users. Threats like SQL injection and buffer overflow attacks are extremely common in the industry, and we aim to prevent attacks like these. If you look at the diagram on the right, you can see how security is layered throughout our entire system, from physical security all the way to the application layers. Our defense system is robust, with many layers ensuring optimal protection. Okay, so let's take a look at our threat matrix. The matrix shows that both priority level and the likelihood of different risks occurring. High priority, likely threats require immediate mitigation through our coding standards. These include things like buffer overflow, input validation, failures, and insecure data transmissions. The other side shows low priority, unlikely risks that are still monitored, but they require fewer resources. We've got things like gaps in code documentation, style inconsistencies, and minor compiler warnings in that category. Knowing the likelihood and severity of each risk is important to prioritize solutions. So, what are our 10 security principles? Let's all start with buffer overflow prevention. We never use out-of-bound pointers or erase subscripts. For memory management, we free dynamically allocated memory when it's no longer needed to prevent leaks. For input validation, we ensure that every input is validated and also sanitized. Error management, we ensure that we don't simply suppress or ignore checked exceptions. Data encryption, sensitive information is never coded to ensure that it is not breached. Access control and least privilege. For this, we will constantly monitor accounts and credentials and authentication and use least privilege principles. Secure network communications. All network communications must be secure using proper protocols like TLS to prevent interception and man-in-the-middle attacks. Code quality and defense programming. We will maintain high code quality and standards and write defensive code that anticipates potential issues. Classes that define an equals method must also define hash code method to ensure data integrity. Secure random generation. We generate strong random numbers for security purposes, never relying on weak or predictable random numbers. RAII and resource management. We will allocate and free memory at the same level of abstraction to maintain clean resource management and prevent resource leaks. Okay, so let's get into our coding standards. Each of these ties into those principles that I just mentioned above. Buffer overflow prevention is severity high, likelihood likely, and priority high at the P18 level. Memory management with RAI is severity medium, likelihood probable, priority medium at P12. Input validation and sanitation is severity high, likelihood likely, priority high at P27. Exception handling and error management is severity medium, likelihood likely, priority medium at P18. Data encryption at rest and in transit is severity high, likelihood probable, priority high at P18. Access control and least privilege is also severity high, likelihood probable, priority high at P18. Access control and least privilege is also severity high, likelihood probable, priority high at P18. Secure network communications are severity high, likelihood likely, priority is also high at P27. Code quality and defensive programming with severity high, likelihood likely, and priority high at P18. Secure number generation, high severity, likelihood probable, priority medium, P18. RAII and resource management severity, medium, likelihood probable, and priority at P12. Okay, let's talk about our encryption policies. Encryption is extremely important here at GreenPace. Let me break down our three-part encryption policy. First, encryption at rest. Any data stored in databases or other data storage must use AES 256 or stronger encryption to prevent unauthorized access and security breaches. Then, in second, encryption in flight or in transit. All data that's moving through our systems must use TLS 1.2 or higher in flight or in transit. This helps prevent any form of interception. And third, encryption in use. Operations that contain sensitive data must remain encrypted during the process to ensure there are no memory attacks or unauthorized users accessing the sensitive data during runtime. These three layers ensure that data is protected at every stage of its life cycle. Now, let's talk about our AAA policies, which include authentication, authorization, and accounting. Authentication verifies the user and the system use multi-factor authentication, and passwords must be complex with a certain length requirement. Authorization controls which users have access to what using role-based access control. We give minimum permissions to users. Only the minimum amount of permission needed for each user to access the data they really need. Accounting tracks and logs activities which help us investigate security breaches and ensure compliance, and also that we meet regulations. These three components work together to create a comprehensive access control. Now, let's talk about our unit testing. This is one of the key measures GreenPace takes to ensure user and client security. We're specifically looking at STD03CPP, which is input validation and sanitation. Our unit tests are designed to ensure that our input validation implementations meet security standards and effectively prevent vulnerabilities like SQL injection. By testing these security controls at the unit level, we catch issues early in the development process before they can become a major problem in production. Now, let's dive into our test cases. Let me show you a positive test case first. We're testing if the function properly accepts valid user input. The code sets up a test called SQL injection test with accepts valid input. We create a valid input string called boots. Then we expect the validation function to return true, and we expect no exceptions to be thrown when executing the query with that valid input. We then run this test with this input of boots, and the result is that it is accepted and it will execute successfully. So this test will pass. To take this further, we'd want to test multiple username formats and special characters to make sure it applies in all cases. Now, let's take a look at a negative test case. This one tests whether the function properly rejects a classic SQL attempt. The code creates a test called SQL injection test with rejects Boolean injection. We set up a malicious input string using the OR1 equals 1 pattern, which is a common SQL injection technique. We expect the validation to return false, and we expect the system to throw in a security exception when someone tries to execute the query with the malicious input. The test input is OR1 equals 1, and the result is that it rejects the authentication attempt and the test passes. Taking it further would look like using or A equals A or other common SQL injection techniques. Let's take a look at another negative test for drop table injection attempts. The code sets up rejects drop table injections test with a malicious input that tries to drop the user's table. We expect the validation to return false, and we expect it to throw a security exception. When we test with the input admin drop table users -- the result is that the input gets rejected and the test passes. To take this further, we test with drop database and test truncate table, which are common injections. This positive test checks whether the function can handle special characters safely without breaking. The code creates handle special characters safely tests with a legitimate input that includes an apostrophe, like boots, boot apostrophe s. We expect the validation to return true. We execute the query with that input, and we expect the result to equal boot apostrophe s. The test shows that we can accept characters like apostrophes without breaking and therefore passes the test. Taking it further, we'd want to test multiple characters like %signs, hashtags, and any other symbols. Now, this negative test looks at SQL comment injection attempts. The code test rejects comment injection with a malicious input that uses the comment syntax user -- We expect false from validations and a security exception when trying to execute. When we run the test, it successfully rejects the comment-based SQL injection and passes the test. To take it further, we can test with hashtag symbols. Our final negative test checks for union-based SQL injection. The test is called rejects union injection and uses a malicious input that attempts a union select attack to pull data from the user's table. We expect a validation to return false and throw a security exception. The result is that it successfully rejects the union SQL injection attempt and the test passes. To test further, we'd want to test with different data types in the union and use SQL injection scanners to find edge cases we may have missed. Now, let's take a look at how automation fits into our security pipeline. This diagram shows the complete DevSecOps lifecycle. We start with the assessment and planning phase, where we're looking at the threat landscape, regulatory changes, change impact analysis, prioritizing our backlog, and responding to new threats. Then we move to the design, where we're incorporating security tests. During the build phase, we're doing secure builds, managing trusted repositories, and securing our open source usage. Verify and test includes vulnerability scanning with digitally signed and trusted sources, functional testing, and compliance and security testing. Then we transition into health checks by configuring and deploying with the right security settings and running penetration tests. In the production phase, we monitor, detect through log collection, SIM, analytics, event alerting, and intrusion detection. We also respond by blocking attacks, turning off services, and rolling back when needed. Finally, we maintain and stabilize by assessing against our security baseline and returning to a stable state after any attack or compromise. This creates a continuous loop of security management. The DevSecOps pipeline integrates security practices throughout the whole development process. The phases of the lifecycle include plan, code, build, test, release, deploy, operate, and monitor. Integrating security practices throughout the process ensures it's not an afterthought, but built throughout the entire process. Let me reintroduce the stages and the tools we use for each. In the code stage, static application security testing helps detect vulnerabilities early. During the build phase, we use dependency vulnerability scanners to check our third-party components. The test phase incorporates dynamic application security testing to find runtime issues. At release, we're using container verification tools to ensure our deployments are secure. During the deploy stage, we use infrastructure security scanners to check our configurations. And in the operate phase, we leverage security information and event management tools to monitor everything in real time. Each stage has specific tools that automate security checks and create the continuous feedback loop. Now, let's talk about risks and benefits. The problem we're addressing include vulnerabilities discovered late in the process, slow releases, lack of compliance, and security breaches. Our solutions are automated security testing and integrated compliance during development, which leads to faster remediation of risks. If we act now, the benefits will aid us more. We can reduce breach risks, meet compliance requirements, and gain competitiveness against competitors who don't have as strong security. But if we wait, the risks become more severe. Increased breach probability, higher remediation cost, and lack of security implementation that leaves us vulnerable. The gaps in our current approach include over-reliance on automation, which means our development and testing teams need proper training. Our recommendation is to act now by starting a pilot project, deploying scanning tools, and investing time and resources into security training for our developers and our test teams. So, our recommendation. Based on everything we covered today, here are our key takeaways. The problems we face currently include insufficient training, inconsistent tool usage across teams, undefined security standards, and a lack of security protocols. Our recommendations are pretty straightforward. We need to establish comprehensive security policies and standards. We need to reinforce the following of these principles by providing adequate training for all our teams. We need to create an effective and robust security protocol that everyone understands and follows correctly. And we need consistent tool usage across all teams so we're not creating gaps in our security coverage. This is crucial to the success of Green Pace. To wrap everything up, here's what we need to prevent future security issues. Automated security scanning needs to be standard across all projects. We need to adopt secure coding standards consistently. OWASP guidelines should be our foundations for addressing common vulnerabilities. And we need to implement a comprehensive cybersecurity framework that covers all aspects of our security posture. The focus of the company should be to have proactive security and not wait until we're attacked. We can act now by starting and integrating the suggestions I have outlined, ensuring that we take real steps into preventing security incidents that can hurt the organization. This isn't just about compliance. It's about protecting our business, our reputation, and most importantly, data, including our own data and client data. Thank you for joining us today.